Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called High Power, coordinating math models. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. The coordination of two types of models is studied: economic dispatch and unit commitment, and competitive electricity markets. Electricity system and wholesale market optimization models make up a flexible decision support system that provides different types of services in an integral way. They can be classified into integrated dispatch of generation plants, optimization of generating agents, and predictive analytics of stochastic processes. High Power is a decision support system that has been developed to support the decision-making processes of agents participating in the electricity and/or natural gas markets. High Power is composed of a set of optimization models that describe the supply/demand process of electricity and natural gas. From this point of view, it determines the partial equilibrium point of the electricity and gas markets under conditions of economic efficiency. The models developed by HI for electricity wholesale systems and markets are dispatch models, economic perfect dispatch, economic regulated dispatch, Carnot-Nash equilibrium dispatch, electricity and gas dispatch, and unit commitment. Complementary models, electricity dispatch and financial analysis, maintenance of regional national grid, electricity supply chain design, and risk management, and energy trading and risk management. Four models are considered fundamental to support the strategic, tactical and operational decisions of an agent that operates generation plants. Traditionally, the optimization models in the electricity sector have been individual modeling with exogenous coordination between models, based on multi-stage stochastic programming, and using large-scale optimization methodologies. The differences provided by High Power are integrated holistic modeling, scientific risk modeling, multidimensional uncertainty, parallel optimization, and autonomous real-time distributed optimization. The video. High Power. Autonomous optimization software for electric sector enterprises. Presents more information about High Power. Operational planning and unit commitment. A well-known activity in the electricity sector is the coordination of two fundamental models: economic dispatch, or operational planning, DP, and unit commitment, UC. Three types of connectivity of the generation system and the transmission power grid are considered: ideal single node, ideal dispatch ignoring the transmission system. Electric transmission network connectivity based on the detailed connectivity of the electricity transmission system using bars and circuits. Operative areas connectivity, when the user does not have, or does not want to use, the detailed configuration of the electricity transmission grid. It is possible to use the connectivity based on operational area //app. Blaster online. com/speech low/changelogs including limits on the transfers between areas. Interconnection electricity. Gas integrates electricity network with natural gas network. Interconnection electricity. Water can be fully detailed, including travel times between nodes and transport restrictions in water resource conduction channels. Unit commitment, UC, associated with short-term operational planning decisions, such as the optimization of detailed distribution by the hour or for shorter periods, respecting all the constraints of the nonlinear and discrete system. The UC model is a mathematical problem that can be converted into nonlinear nonconvex mixed optimization, which implies that it requires a special effort for its solution, since its real-time characteristic does not allow unfeasible approximations for its solution. On the other hand, it is necessary to coordinate the UC model with a medium-term planning, DP, model, which establishes the boundary conditions, in such a way that the state of the system at the end of the UC problem be the same as at the beginning of the DP problem. Ideally, a single model should be solved, which would allow the system to be represented in detail throughout the planning period, that is, solving a long-term scheduling problem. During periods 1 to t. For complex systems, this may not be computationally viable. However, for not-so-complex systems the alternative could be viable, considering the computational capacity offered by Industry 4.0. For this reason, conventionally it has been considered necessary to resort to the integration of both models, UC and DP. You should consider the implicit approaches involved in such a decision. Based on the vision of the artificial hypothalamus, building a monolithic model consists of cutting and pasting equations, and thus obtaining the optimal solution, regardless of the type of dispatch model that is appropriate according to the market. The solution of the monolithic model can be realized with large-scale optimization methodologies. An alternative, the simplest, is to combine the two models into one and solve it completely, without resorting to model coordination schemes. To this end, the planning horizon is divided into two periods. 1 to TCP, modeled as a UC problem, and TCP plus 1 to T, modeled as a DP problem. In this case, the integration is carried out using the system state variables, the inventories at the end of the TCP period of the UC model, with the initial inventories of the DP model. This involves introducing equality constraints to enforce the coupling. This model could be used to carry out short-term programming, with medium-term planning. The traditional thing has been to divide the process into two models. Stochastic economic dispatch model, oriented to planning activities, and deterministic model of unit commitment, oriented towards real-time scheduling. The coordination of both models is essential for the results obtained for the real generation. The traditional way to approach the problem is to coordinate the two models, solving each independently, offline, so that the office planning model, DP, establishes the boundary conditions of the office scheduling model, UC, which can be interpreted as the optimal planning objectives. This approach may not have a viable solution in the UC, because the differences and/or approximations could lead to the non-viability of the set of objectives established by the DP for the UC. There are two alternatives to carry out coordination. Coordination through economic variables, dual variables or prices. To this end, the opportunity value of inventories is set at the end of the period TCP, or at the beginning of the first period. In this case, it corresponds to the value of the water. The application of this approach should be careful, as boundary conditions should reflect variation in prices between periods, but in general, only a sample of the value of water is considered, at the beginning or at the end of the planning horizon. This can lead to water value profiles, which are far removed from the profile estimated by the DP model, which is never observed in the UC. This approach always offers viable solutions, but they may be far from optimal due to the distortion of the dynamic price profile. Coordination through physical variables, primal variables or quantities. To this end, the quantities of resources to be used and the quantities of industrial products to be produced during the period of operation of one to the same period are established. The inventory levels that must be reached at the end of the period, the TCP moment, are also established. This approach does not distort the dynamic price profile but may not have a viable solution due to the small differences between the two models. Non-feasibility, which can be managed by soft constraints, which introduce penalized slack in the target function, to ensure that the final schedule is close to the optimal target set by the planning. The chaining, or coordination, of models does not guarantee optimality, because there are always at least two alternatives to concatenate two models. By quantities, or primal variables, such as water use, or resource use in general, or by prices, or dual variables, that is, the value of water, or in general the value of resources. Cyclical coordination can produce the optimal solution, or correct unfeasible solutions. The integrated model can be solved using large-scale techniques, such as Bender's partitioning and Lagrangian relaxation. This approach reduces solution time and memory requirements. High power competitive electricity markets. Nash-Carnot and Stackelberg equilibriums. High invites you to watch the video. The Roots of AI, Game Theory. The ED, Electricity Economic Dispatch, model optimizes the dispatch of generation infrastructure, minimizing the cost of operating the electricity system, which simulates a perfect electricity market. EAT is the core model of high power, as its equations/constraints are used in multiple specific models that the agent requires to address decision support needs. From EDD, 3 models of complementary dispatch are built: economic perfect dispatch, economic regulated dispatch, Nash-Carnot equilibrium dispatch, and unit commitment. The first 3 models are oriented to planning and the fourth to real-time programming. Economic regulated dispatch, delivery of plants that minimizes the cost of operation of the interconnected system and includes representatives aspects of the regulatory of the electricity market being simulated. It does not correspond to a model of economic equilibrium, however, it is an easy and fast way to represent regulatory considerations based on optimization models. The central highest power model is the integrated representation of electricity and gas supply chains. From the basic equations, variations of the model are generated, according to the techno-economic concepts that support a specific use case. The E&G equations represent the physical dispatch of an electricity-gas system, regardless of the market in which the system is located. The main variations of the dispatch model are related to the representation of the market where the power system operates. The process simulates an integrated system in which the two markets, gas and electricity, are balanced according to their operational assumptions. As for consumers, models tend to assume an inelastic behavior of demand with respect to price. This hypothesis can be relaxed by modeling a target function with variable demand, where the economy's social surplus is maximized. This is for any type of electricity and gas market. For the gas system, gas supply and transport contracts can be incorporated, as this type of commercial instrument is commonly used in the gas market and affects its operation. The main models in the electricity market are economic dispatch, EED, dispatch of electricity generating plants, minimizing the cost of operating the interconnected system. It simulates a market that assumes perfect competition between generators. It is the company that is traditionally used when the market is model controlled. Regulated economic dispatch, ERD, dispatch of plants that minimizes the cost of operation, plus the regulated cost of the electricity market, i.e., the costs derived from market regulation decisions. As a starting point, the traditional economic dispatch model is used, which includes the equations of regulatory costs or revenues. The extended model is equivalent to a low-cost dispatch model, considering operational costs plus costs arising from regulation. The new model has 2 types of variables and restrictions, those of physical dispatch, EANG, and those derived from the regulated market. This model assumes perfect competition between generators. The difference is that they are informed and rational generators, which include as part of the analysis the costs or benefits derived from regulation. The non-inclusion of regulated costs implies an erroneous analysis, which should lead to biases in the user's decisions. The high ERD model can be used too. The agent's decision-making, same as with the simple economic model of dispatch, but using a better approach, and analysis of the impacts of regulatory proposals, valid for any of the authorities and market agents. Ignoring that the regulation affects the firm seems a naive position. Nash-Carnot equilibrium dispatch, NCD, dispatch of plants oriented to the simulation of competitive electricity markets, with agents that can influence the transactions that occur in the market, usually through price and/or quantity offers. 2 types of agents are considered, those who make prices and those who take prices. The best way to visualize the model of the NCS is to break it down into its parts, each of which is a mathematical problem. The first model represents the inelastic demand, or non-demand, that accepts or does not accept generator offers. This model represents society. Normally this function is performed by the ISO, interconnected system operator, which assumes the function of implementing the optimization process, through a spot market model with physical and commercial restrictions. Depending on the regulations, you can define prices, or quantities, or prices and quantities. In the second level, there are generators that make their offers, which are sent to the ISO, which decides which ones to accept, which to reject, and defines the spot price. Market equilibrium is achieved in an iterative process. This is a form of market common in competitive markets, based on offers from agents. It must be considered that equilibrium, the optimal for society, is achieved in an iterative process, and never in a process of a single pass. If it becomes so, it would be a coincidence. Solution methods can be Lagrangian or Bender's coordination, and mathematical programming with equilibrium constraints, MPEC. In competitive electricity markets, generating agents form a Stackelberg-type oligopoly, in which there is a small group of dominant agents and the rest are dominated agents. The former have the power to define prices, the price makers, and the latter, the price takers, must accept the prices defined by the dominant agents. By organizing a three-tier model, you can determine the break-even points for this type of market. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.